want to welcome Professor and Dr. Nirshviv from the, I have to look here, I have the pronouncement announced for me, but I'm not sure I can say it right, but it's Rakach Institute of Physics. I hope you are satisfied. And he's from the Hebrew University of Jerusalem. And we are very happy and proud to have Nirshviv here to have a talk about, I'm going to read the title, which is Nothing New Under the Sun and the Sun's Lasting Role in Climate Change. So, and I would recommend you after this talk to ask questions directly to Nirshviv. And actually I also want to tell the audience that Nirshviv and his family has just presently arrived back from Princeton, the Institute of Advanced Study, and yeah, the famous Einstein were there, working there, so we are very proud to have you here. Welcome.
First of all, it's a pleasure being here. Hear me? Can you hear me? Okay, good. It's actually interesting because you mentioned Einstein, and you couldn't pronounce my department name, but Einstein, when he died, he actually left all his intellectual property to the Hebrew University, so not to the Institute for Advanced Study. Okay, so I'm going to talk about climate. And I'm going to talk about the effects of the sun, and I'm going to talk about three particular things. I didn't do that. Okay, three particular things. I want to first review and show you that the sun has a large effect on climate. Then we will want to quantify it. I will also want to show you that once we understand that it's relatively large, I want to discuss its implications to the understanding of 20th and 21st century climate change. And then I'll want to end, the third part is going to be a short discussion on the evidence showing you that the link between climate and solar activity is actually through something called cosmic rays. Okay, so this is what I'm going to talk about. I'm going to show you that the sun has a large effect on climate. We're going to quantify it. I'm going to show you that it is important to understand 20th century climate change. It has probably contributed something like half of the temperature increase over the 20th century, but it also allows us to see the 20th century and 21st century, or climate change in general, with a fuller picture in which things fall into place much more, much nicer. But in particular, it falls into place with a climate sensitivity which is on the low side, namely changes in the energy budget that are associated either with solar activity or with human activity are on the low side. For example, if you double the amount of CO2, it will increase by only a small value. And as I said, I'm going to end with discussing the cosmic rays. Okay, so now if you suddenly have a seizure or something and you don't remember anything else, these are the takeaway points, and that's it. Okay, so let's begin. First of all, the sun has a large effect on climate. To begin with, the sun is variable. This here is, for example, the sun in UV. This is when the sun is in solar minimum. This is when it's in solar maximum. If we look at the sun, we can see things like sunspots. The number of sunspots varies with a quasi-periodic 11-year cycle. Here you can see in X-rays places where the sunspots are, they're more luminous, and things like that. So the sun has a lot of non-thermal behavior, and this behavior changes by quite a lot over a cycle of 11 years. Basically what happens is that every 11 years, the north and south magnetic pole of the sun switch polarity. So the full cycle is actually 22 years. And the interesting thing is that there are a lot of things which vary together with it, the sunspots, the strength of the solar wind, the magnetic field of the sun, the amount of UV that the sun emits, and so forth. And another important thing is that in addition to this 11-year solar cycle, we have variations in solar activity on longer time scales. Sometimes the 11-year solar cycle is stronger, and sometimes it's weaker. And sometimes, like during the latter half of the 17th century, it was particularly inactive. And that was also a period of the Little Ice Age here in Europe, right? I think the Swedes could cross, right? And it wasn't a good time for Denmark because of it. I think so. So there are long-term variations, but there are also very short-term variations. Like sometimes you get field lines close and you get a gust in the solar wind. So we'll see that on all those timescales, there are variations in the sun and concurrently on Earth in the climate. Okay. This is probably one of the nicest examples I know, showing you, on one hand, a proxy for solar activity. At the top, you see the amount of carbon-14 derived from tree rings. And this is a proxy of solar activity because carbon-14 is formed in the top of the atmosphere by spallation. You have high-energy particles come from outside the solar system. They're called cosmic rays. And they hit the top part of the atmosphere. They form secondary products like carbon-14, which is, in this case, radioactive. But the flux of those cosmic rays is modulated by solar activity. When the sun is more active and it has a stronger solar wind, less of these cosmic rays can reach the Earth. So we form less spallation products, and in particular, less carbon-14. So by looking at the amount of carbon-14 as a function of a year in the tree rings, you can know what solar activity was. So this is a proxy of solar activity. On the other hand, here at the bottom, we have a proxy for climate on Earth. In this case, we're looking at the oxygen 18 to oxygen 16 isotope ratios in stalagmites in a cave in Oman, in the southern Arabian Peninsula. And this is a proxy for climate because water with oxygen 18 is heavier than water with oxygen 16, which means that the evaporation rate from the oceans is different, but it's going to be temperature dependent. So this thing basically is a proxy for what the temperature of the Indian Ocean is, because that's where the monsoon water going to those caves came from. Okay, so you see a proxy for solar activity and a proxy for climate, and I think there is a nice correlation. Okay, so most likely the sun affects the climate. I don't think it's vice versa, that the climate affects the sun. You think so? I don't think so. Okay. Here is another example from the northern Atlantic. You see, again, the carbon-14 in blue. And in black, you see evidence for whether it was cold or warm in the northern Atlantic, because in colder periods, you have ice-rafted debris carried to southern latitudes, and as this ice melts, it leaves this debris on the ocean floor. So by digging cores from the ocean floors, you can know whether it was colder or warmer. So you see that there's a very nice correlation. And you can see this kind of correlations between solar activity and climate everywhere on Earth, in many places, implying that in a lot of places on Earth, there's a very strong influence of solar activity on the climate. Going on shorter timescales, in fact, the first person to think that there is a correlation between solar activity and climate was Sir William Herschel, and he didn't have a very good temperature proxy, so what he did, he looked at the price of wheat in the London Wheat Exchange and tried to see whether there's a correlation between that and a sunspot number, and according to him, there was. Going forward 200 years, this is probably the first paper that in modern times that someone considered that the sun has an effect on climate. And here you see the severity of winters in Europe. Again, this is the Little Ice Age. And at the bottom, you see some proxies for solar activity, and you see that the Little Ice Age was when it was the sun was particularly inactive, or during the medieval times when Vikings could encircle Greenland and call it Greenland, the sun was active. Well, probably they called it Greenland for PR purposes, like come and settle down Greenland. And then people came there and they were a little bit surprised. Okay, on shorter timescales still, you can see here in red, you can see solar activity. So you can see the 11-year solar cycle. And in black, you can see the rate of change of the sea level based on tide gauges. Okay, so you can clearly see that every time the sun is more active, the oceans tend to expand. And the reason is that they absorb more heat and they expand thermally. Okay, so the previous examples were qualitative in the sense that they can be used to show you that there's a very clear link between solar activity and climate. But in this case, because we know by how much the oceans should expand when they absorb a given amount of heat, we can actually calculate and quantify the effect that the sun has on the climate. Okay? So this allows us to use the oceans as what's called a calorimeter to measure the amount of flux, the amount of heat that we get from the sun in sync with the solar cycle. It turns out that this amount of heat is much larger. It's about 7 times larger than what you would expect from just changes in the solar irradiance, from the solar luminosity over the 11-year solar cycle. So there must be some kind of another amplifying mechanism. This was based on tide gauge records, which ends roughly at this time, but you can actually see with the altimetry data the same thing. Here in blue, we see the linearly detrended sea level change, and in purple, you see a fit, which includes El Nino southern oscillation and solar activity, and you see that almost all sea level change on this time scale, except for the linear trend, which is associated with the melting of ice caps, you see that all those variations, or a large fraction of them, are associated with the sun and El Nino. Okay, so what else do we have? We also have that with the 11-year solar cycle, we see changes, in this case it's a cosmic ray flux, but it's a proxy of solar activity, and we see changes in the low altitude cloud cover. Why is it interesting? It's interesting for 2 reasons. First, as we shall see in the third part, it actually allows us to, or it is related to the mechanism itself associated with linking solar activity and climate. The other interesting reason is that we have satellite data with which we can quantify the change in the energy budget on Earth associated with this change in cloud cover. The interesting thing is that this change in energy budget is exactly, or consistently the same as what you see goes into the oceans every solar cycle. What does it mean? It means that the sun has a large effect on climate. The effect can be quantified, and it's very large, and we see where it comes from. It comes from the fact that the cloud cover changes with the 11-year solar cycle. Okay? Okay, so you can quantify the change in the solar radiative forcing in watts per square meter over the solar cycle, and you can use, I showed you the tide gauge record and the satellite data, and you can use the cloud variations and satellite data, and you can use other measurements, and you can consistently show that the sun has a large effect on climate. This is the change that you would expect from just changes in the solar irradiance. Observations, what people usually take in climate models. So one thing we know is that the real effect of the sun is large, and it means that climate models should include it. The other thing is that we should think very carefully what is the mechanism responsible for this large effect. Okay. Second part. We know that the sun has a large effect on climate. We now want to understand what does it imply for understanding 20th century climate change. In standard models, those that you would find in, say, the IPCC reports, we try to explain 20th century climate change, we know that the temperature increased by about 0.8 degrees over the 20th century, with mostly anthropogenic forcing, the fact that we pumped CO2 into the atmosphere. CO2 is a greenhouse gas, it changes the energy budget, and therefore it should cause some heating. Now, in order to explain this 20th century warming with the energy budget that is mostly anthropogenic, we need a climate with a relatively high sensitivity. Namely, that if we double the amount of CO2, the temperature will increase by a lot. If we change the energy budget because of the sun by 1 watt, the change in temperature is going to be large, and so forth. But this high climate sensitivity will then imply that a given change, some scenario, emission scenario over the 21st century, will necessarily give you a large temperature increase over the 21st century as well. But if the sun has a large effect as well, and we know that solar activity increased over the 20th century, if we now include the anthropogenic forcing with the solar forcing, which is actually comparable, we find that in order to explain the 20th century, we now need a low climate sensitivity. And this low climate sensitivity will imply that the same emission scenario over the 21st century will now give you a temperature increase which is on the low side. How much? Well, we can model it. This is an example for a model which includes a lot of things. We can try and fit the 20th century. And in fact, when you do that, you find that if you include the large effect of the sun, you can explain the 20th century with typical residuals, which are half as much as what IPCC scenarios give you, or IPCC, or models employed by the IPCC. Because these models don't include the sun. Okay, if you include the sun, you can explain 20th century temperature change much better. You can then use the models and integrate forward in time, and for different reasonable realizations, ask the question by how much the temperature is going to increase in those models where you include the sun into account, and then you can compare that to the IPCC models. Okay, so my best estimate is the temperature increase is going to be about 1 degree over the 21st century under a vanilla-flavored scenario. Okay, a little bit about climate sensitivity. This is, if you open the IPCC reports, for the first report, the second report, the third report, and so forth, this is the range that they claim that Earth's climate sensitivity should be. And in fact, it all dates back to some federal committee that sat in 1979 in the US, the Charney Committee. And since then, they claim that it's between 1.5 and 4.5 degrees. What I claim is that if you include the sun into account, you find very consistent sensitivities, which are typically like that. I can give you a few examples showing you that the sensitivity should be on the low side. Here you see the temperature increase over the past 30 years. And given that the IPCC scenarios are basically the same since the first IPCC report in 1990, it means that if those models were correct in 1990, and they should be still correct, and the temperature today should be within the predictions made in 1990. Are they? Well, we see here that they're not. The temperature, this is the range of predictions made in 1990 with models saying that the sensitivity should be 1.5 to 4.5 degrees. And this is what the temperature has done in real life. What does it tell us? It tells us that those scenarios with a high climate sensitivity are inconsistent with the actual data. So what should you do? You should modify the models. This is not exactly what the IPCC does. What the IPCC does is it resets its prediction clock every 6 years. So you're always within the range of predictions. On completely different time scale, here you see 500 million years of geological data. And here you see the CO2 in the atmosphere. And this is a logarithmic scale. So for example, 450 million years ago, you see that there was about 10 times as much CO2 in the Earth's atmosphere. If CO2 has a large effect on climate, like a 5-degree increase per CO2 doubling, then surely this should have reflected itself in the temperature reconstruction. But here at the bottom, you see the temperature reconstruction, and do you see any correlation between the two? No. The fact that there is no correlation between the two can be used to place an upper limit on climate sensitivity, one which is about 1.5 degrees per CO2 doubling. Okay, and then of course the 20th century, if you want to fit the 20th century with the sun, you find that the sensitivity should be on the low side. Okay, so now a few minutes for the third part. What is the actual link responsible for linking solar activity to climate? The answer is cosmic rays. So what is the relation? I told you about cosmic rays. These are high energy particles which come from supernova remnants. Supernovae are massive stars. If you have a star which is, say, 10 times more massive than the sun, when it dies in a big explosion, and it ejects its envelope at high velocities, as much as 1/10 the speed of light. And the shock waves between this envelope and the interstellar medium accelerates particles to high energies, and then they diffuse around in the Milky Way, and they can reach us. And those cosmic rays are the dominant source of ionization in the atmosphere. Okay, here you might have, this is not concrete. Here you might have a radon coming from the concrete. This should be concrete. So you might have ionization dominated by radon. But everywhere else in the troposphere, in the lower part of the atmosphere, the ionization is governed by those high energy particles from supernovae that exploded typically 10 million years ago. Now, as I also told you, those cosmic rays are modulated by the solar wind. When the sun is more active and the wind is stronger, less of those cosmic rays can reach the Earth, and with it, the ionization in the atmosphere decreases. By how much? Over the solar cycle, the rate of ionization changes by something like 10–15% in the bottom few kilometers. Now, today we know that these ions play an important role in both the formation of small aerosols and their growth into larger aerosols, large enough such that when you reach 100% humidity, water has surfaces upon which they can condense and form clouds. Okay, so today we have evidence showing you that all those things work. And if we change the properties of the clouds, we will change, like if we make the clouds whiter, we will reflect more of the sunlight, and that will change the energy budget. Okay, so a little bit about the evidence. This is a group here at DTU. What we see here are several day-long reductions in the cosmic ray flux associated with what's called Ford-Bush decreases. That's gusts in the solar wind, which causes a reduction in the cosmic ray flux. And here you see various different parameters. This is the number of aerosols in the atmosphere. Sorry, this is the size of the aerosols. This is different cloud data sets showing you that the clouds react to those reductions in the cosmic ray flux due to the solar gusts. On much longer timescales, which is actually the way I entered the field, you see something else. As I told you, cosmic rays come from supernova remnants, but they're not distributed homogeneously around the Milky Way. In fact, because they come from stars which live a relatively short lifetime of only several tens of millions of years. It means that different places in the Milky Way have different densities of cosmic ray flux. And as we rotate around the Milky Way, sometimes we see larger fluxes of cosmic rays, and sometimes we see lower fluxes. If cosmic rays affect the climate, we should see a correlation between this cosmic ray flux and climate on Earth. Now, because variations of our solar activity give rise to a 10–15% change in the ionization where the clouds form, but the change in the cosmic ray flux density over geological timescales is expected to be a factor of a few. Instead of a 1 degree effect, which is what we have associated with solar activity, in this case, we should expect variations of, say, 5 or 10 degrees. These are huge variations and should be enough to push Earth completely out of ice ages or into deep freezes. So, is there a link? Okay, so as we rotate around the galaxy, we pass through spiral arms of the galaxy every so often. That's where most of the star formation takes place, and therefore most of the cosmic ray acceleration. And we should witness higher fluxes of cosmic rays at those points. At the top, you see a reconstruction of the cosmic ray flux using iron meteorites. Meteorites are exposed to cosmic rays, and they accumulate spallation products. So from them, you can actually reconstruct the cosmic ray flux. At the bottom, you see, again, the cosmic ray flux in red, and in black, you see the temperature reconstruction based on oxygen-18 to oxygen-16 isotopes in brachiopods, in this case. Those things. Okay, in fact, I mean, this here, you can, over the past half billion years, you can reconstruct a quantitatively the temperature, but over the past billion years, you can see that every about 150 million years, there were ice age epochs on Earth, and you can continue this reconstruction for the past billion years and see that there were 7 increases in the cosmic ray flux over the past billion years, and they all correspond to ice age epochs on Earth. On a slightly shorter time scale, okay, so here you can have the temperature reconstruction, and here you see the 150 million year period associated with passages through the spiral arms. On a shorter time scale, you see these oscillations. Okay, you can massage the data, remove the the 150 million year oscillation and the linear trend, and then bin it, and you get something which looks like this. This is the temperature after you move the 150 million years. On shorter timescales, you should expect something in addition. Not only do we pass through spiral arms every so often, but we also cross the galactic plane every about 32 million years. Okay, so what else do we expect? In addition to the variations due to spiral arm passages, we expect that every time we pass through the galactic plane, when it is colder, when there is more cosmic rays, it should be colder on Earth. So we should see a 32 million year oscillation in the temperature data. And this is what you get from theory. You can actually fold the data over 32 million years, like an old analog TV. So this is time folded over 32 million years, and this is time. So you see that there's a phase where it was cold and phase when it was warm on Earth. And you see the 32 million year oscillation. But the interesting thing is that you see a secondary oscillation in the data. This secondary oscillation is consistent in phase and period with the fact that we are not rotating in a circle around the galaxy, but sometimes we are closer to the center of the Milky Way. The density is higher and we're oscillating faster, and sometimes we're further out. So you can see all the galactic motion in the geological data. Okay, so we have lab measurements taking place in the Sky Lab here at DTU. Well, that was actually before you moved to DTU, right? So you can see that when you increase the ionization, you increase the nucleation. This experiment was repeated at CERN, and surprise, surprise, they found the same thing. You can show that you increase the growth rates from CNs to CCNs. You can Google something called ship tracks and show you that wherever ships pollute the atmosphere by burning dirty fuel, those exhaust particles serve as cloud condensation nuclei. So you can see that if you increase the number density of cloud condensation nuclei, you change the properties of clouds. Okay, so everything in this is known. And with this, I'll end. We see that the sun has a large effect on climate. We can quantify it and show that something should be amplifying the solar activity. It cannot be just changes in the solar irradiance. The effect is most likely through a cosmic ray flux modulation, and it's important, but people ignore it. Why? I don't know. Okay, so this is all.
Thank you very much, Shiviv. It was very exciting, and I would say that because time is a very important factor in your work while you're in Denmark, I'll recommend you to just, let's say, have questions in a period of maximum 5 minutes. Is it okay?
I don't care.
Okay, fine.
Hello, hi. Can you quantify the effect of the single supernovas in this work? Because we have a few examples of nearby supernova, and they, in principle, should leave a trace also if the cosmic ray is this effect.
It's an excellent question, but the answer is it's very hard. The reason is that if you look at very recent supernovae, like there was a Tycho's supernova discovered here in Denmark. It took place relatively far away. What do I mean by relatively far away? It takes the cosmic rays a relatively long time to diffuse from that distance to our location. So long that over this time scale, there are actually many supernovae. So we cannot see the effect of a single supernova unless it is really, really close by. In such a case, so in principle, it is possible that over the past several tens of millions of years, there was maybe 1 or 2 supernovae which were close enough such that the cloud of cosmic rays could have given you an increase in the cosmic ray flux for something like 10,000, 100,000 years, which would give you a cosmic ray winter. So we know that those things should have happened, but the question is now whether it is possible to detect them, and it's very hard. One way would be to dig for ocean cores and look, for example, for things like iron-60 or something else which is formed by the supernova. There are some indications that this might have happened, but it's very hard to pinpoint and say that 27 million years ago there was a particular supernova and we could see its effects.
Thank you. Is there any more questions? Yes?
It's more political, actually. You say that IPCC, instead of including solar effects into the weather models, they reset their calculations. Can you give a more specific example? I would assume what they do is they update their models. That's would be their explanations. So, can you say a little bit more about this resetting of the?
Okay. So it's clear that the climate models that we have today, especially those employed by, for example, the IPCC, are much more elaborate and they include much more physics than, say, models which we had in the early 1990s. They're much better, and with them you can do much more than you could do back then. But it turns out that the crucial thing with which you want to predict what will happen, say, in the future is climate sensitivity, and those models are not any better in determining climate sensitivity than they were, how much is it, 25 years ago. You could also see it by their claim. They claim that the range of climate sensitivities is 1.5 to 4.5 degrees per CO2 doubling, which is exactly the same as it was in 1990. So how come, even if the climate models are better, how come this thing is not any better? And the reason that the climate models cannot predict climate sensitivity any better is because The largest uncertainty in climate sensitivity is the way that cloud cover behaves. What do I mean? Suppose we double the amount of CO2. We know that this corresponds to a change in the energy budget of about 3.8 watts per square meter. Now, if Earth didn't have any feedbacks whatsoever, if you just differentiated what's called Stefan Boltzmann's law, you would get that that this 3.8 watts would have given you a temperature increase of slightly less than 1.2 degrees. But if you increase the surface temperature by, say, 1.2 degrees, you evaporate more water from the oceans because the oceans are warmer. And we know that water vapor is an excellent greenhouse gas, so you would want to amplify this temperature increase even more. However, if you have more water vapor in the atmosphere, you will also have more clouds. And the clouds can have a range of effects. And it turns out that the largest uncertainty, the most important parameter determining the climate sensitivity is the way that the cloud cover is treated in the climate models. Because we don't understand the microphysics well enough so that from first principles we can say that if the temperature changes by a given amount, or the water or the humidity changes by a given amount, by how much the cloud cover will change. So the climate models basically have recipes to describe the change in the cloud cover. And this recipe, which is used in the climate models, basically gives you the climate sensitivity of the models. So even though the models today are much more elaborate than they were 25 years ago, the largest uncertainty, which is cloud cover, is still there, and therefore they cannot be used to predict climate sensitivity. Now, as for my remark on resetting the climate predictions, like every 6 years they come up with a new scientific report, and they say, this is what the temperature has been doing in the past, and now we predict what the temperature is going to do in the future. They don't go back to the predictions that they have done in the first IPCC report and say, look, these were the predictions back in 1990, and the temperature today hasn't increased or wasn't in this range of predictions, therefore there's something wrong in our climate models. They don't do that.
Yes, thank you. Is there any further questions? Yeah.
Thanks. The aerosols you mentioned, what are they chemically? May their origin or their precursors maybe because of human origin?
Okay, so you have a range of aerosols. You have what can serve as cloud condensation nuclei. You can have near the ocean, you can have sea salt serve as basis. You can have dust from deserts. But it turns out that probably the most important aerosols are those that are grown from sulfuric acid in water molecules, and sometimes additional molecules like ammonia or whatever, which can facilitate the nucleation and growth. But it's basically, I mean, the most important ingredient in this case is sulfuric acid, which comes from oxidation of SO2, which comes from either volcanoes or oxidation of DMS. Like if you go to the ocean, which is not far from here, and you have this typical algae smell, that's DMS. So,
And
you?
What's the answer of IPCC to your research? I mean, why don't they use your results to improve their model?
Okay, so there are two questions here. What is the, perhaps?
The first one is, what is their answer? Like you,
there's no answer, it's being ignored.
They're ignoring your research at all? Like
look, this paper, this results, this quantification that you have here, where is the graph? This result shows you that the sun has a large effect on climate. Okay, it was published in 2008. The IPCC should have included it in their last scientific report, but they didn't. They ignored it. And it was published in the Journal of Geophysical Research. It's like the mainstream journal in geophysics. It wasn't in some obscure conference proceedings that took place in Bora Bora. Okay? So it's ignored. Why? I don't know. I mean, I can speculate, but
I think the time is running.
it's okay. I mean,
It's again political, and not including significant results could either be discarding it rather scientifically or political. So what would your suggestion be if we, the audience, wanted to put this into a political context so that it couldn't be ignored, at least commented in the next IPCC report?
Yeah, Ulla, I think the time is up.
Yeah. Let's end this session, and thank you for...
No, I was
Okay.
joking because
Maybe we shouldn't record it.
no, I mean, the answer is, I don't know, it's like, blogosphere is filled with, activity, and people do actually understand that, the sun has a large effect on climate, but it still hasn't percolated to, the right, communities. I don't know. I don't have an answer to this question. But they should have said, okay, we don't, Professor Svensmark has his work, and they could think that it's controversial, and you could think that anything I said here about cosmic rays is BS. Still, even if you don't know what the mechanism is, you see that the sun has a large effect on climate, but it's ignored. So even though it's controversial, and it shouldn't be, because, I mean, you saw the evidence, how clear it is, but even if you don't believe a word I'm saying, still there's evidence that the sun is doing or has a large effect on climate, but it's ignored. Why? I don't know. Well, I know, but I won't say.
Would your predictions then be able to, or your model, would that be able to predict sea level rise and temperature rise solely, or is it a contribution to the already existing models?
So it is a contribution, and it is, I mean, I don't know what the sun is going to be to do in the future. Some people say that we think we're entering another Maunder minimum, and therefore there's going to be another little ice age and so forth. I don't think you can predict it. I remember a few years ago, I saw in a conference, not in a conference, someone began his talk by showing all the predictions that people have made for what solar activity is going to be in the next solar cycle, from a solar minimum to, from a very low maximum to a very high maximum. It's like someone saying, these are all the predictions for what the lottery numbers are going to be, and someone is going to win. So I don't think you can predict it. And in this sense, I don't think we can know what the sun is going to do in the 21st century. So I cannot predict this thing. I can give a range of predictions for what the sun could be doing, and with my, I think, better estimate for climate sensitivity, I can try to give you a range for what the temperature changes are going to be, and with it, a range for what the sea level rise is going to be. So I think sea level rise over the 21st century is going to be of order 10 to 15 centimeters. Is it good for Denmark? I don't know.
It depends.
One perhaps a little more technical question. How come the solar wind in itself doesn't create these clouds?
The solar wind, even though it is charged particles, is not, or the energy of the particles in the solar wind is much lower than the energy of the cosmic rays. The cosmic rays come with energies of typically a GeV and more. A GeV means that it's the protons that are beginning to be relativistic, but it's only like 10 GeV protons which can penetrate, or the secondaries can penetrate the atmosphere. So that's an energy of 10 GeV. The highest energy particles in the solar wind is about a few hundred MeV. So it's 1.5 orders of magnitude smaller than what you need in order to penetrate the atmosphere and do anything. So the sun doesn't do a lot in this sense. Oh, sorry, it does do a lot, but it doesn't do directly to the solar wind.
I think we will say thank you to Nirshviv. If you want his contact information, you're most welcome to contact me. My name is Ulla Svensmark. I'm working at the DTU library. So let's give Nirshviv a hand and say thank you for this exciting talk.